In this movie, we will introduce advanced NanoLabo, an integrated GUI for nanomaterials, developed by Advanced Soft Corporation. Also, we will show demonstration of various modeling function of advanced NanoLabo. The structure of this movie is as follows. Firstly, we will introduce features of advanced NanoLabo. Secondly, we will demonstrate how to edit crystal structures. Then, we will demonstrate how to generate slab models, including interface models. Then, we will demonstrate how to generate molecule models, including polymer models. Finally, we will explain product information. Besides, links of each chapter in the description is available. Please note that you can watch articles of analysis cases and demonstration movies of advanced NanoLabo from the link in the description. Now, we will introduce features of advanced NanoLabo. Advanced NanoLabo is an integrated GUI for nanomaterials analysis via first principles calculation and molecular dynamics. The available solvers on NanoLabo are followings. Advanced Phase, which is first principles calculation software developed by our company. Quantum Espresso, which is open source software for first principles calculation. And LAMPS, open source software for molecular dynamics. Main features of NanoLabo are followings. On NanoLabo, you can search and download structure files from the Materials project, an online database. Settings of calculation on NanoLabo can be done extremely easily. NanoLabo has useful and various modeling functions. NanoLabo visualizes calculation results instantly. Moreover, NanoLabo can train neural network potentials when cooperating with advanced NeuralMD, which is developed by our company, and execute molecular dynamics using the trained neural network potentials as force field. NanoLabo will solve these problems. If you are interested in DFT calculation or molecular dynamics but feel hesitant to begin, you can execute calculations immediately on advanced NanoLabo. If you are struggling to editing input files, you can edit them on GUI easily, and default values are set automatically. If you have difficulty to create files of complex structure, diverse and easy modeling functions are implemented on NanoLabo, and enable you to create complex structures such as interface models and polymer models immediately. If you can't be bothered to visualize results on log files, you can visualize results on NanoLabo instantly. We show the list of main functions of NanoLabo version 2.8 here. Various modeling functions and many calculation functions are available. For LAMPS, you can use classical fields, general force fields such as Open Catalyst and M3GNet, and neural network potential trained by advanced NeuralMD as force field. Furthermore, visualization functions, job submit functions, and cooperation functions with Python are available. New feature of version 2.8 is Jupyter interface for NanoLabo. This interface enables you access Jupyter Lab from NanoLabo. You can send and receive structure files between NanoLabo and Jupyter Lab interactively. You can use this function without extra charge until July 31, 2023. Then, we will demonstrate how to edit crystal structures. We use silicon crystal as an example. Now, I search and download silicon structure file from the Materials project, an online database, using Materials Finder on the top right. Then, many structures include only silicon atoms on databases are displayed in several seconds. I select the MP149, which is diamond structured. I select the modeler function from the menu on the bottom left. Then, I open the Crystal tab. In the Crystal tab, you can convert cell type, substitute elements, and introduce lattice defects. If you click the Build button of Finding a Primitive Cell, the crystal structure is converted to primitive cell automatically. Also, if you click the Build button of Finding a Standard Cell, the crystal structure is converted to standard cell automatically. Moreover, if the symmetry of the crystal structure is low, more symmetric cell function enables you to find more symmetric structure, allowing atoms to move within specified threshold of displacement. To demonstrate this, I will move atoms of the structure to reduce the symmetry. So, I open the Atoms tab. In the Atoms tab, you can move atoms, select which atoms to be fixed, and rotate atoms. I select which atoms to be moved and click the Stat Modeling button. You can move atoms in X, Y, Z direction, specifying displacement by the slide bar, respectively. Besides, from the context menu, you can input values directly. Also, from the context menu, you can extend the domain of the slide bar twice. These are the same for other slide bars on NanoLabo. Then, I click the End Modeling button. I return to the Crystal tab. From the Option button of More Symmetric Cell, I set the threshold of displacement as 1 angstrom. Then, I click the Build button of More Symmetric Cell, and the structure is converted to more symmetric structure, namely, diamond structure. On NanoLabo, you can detect space group from the context menu. It can be seen that the symmetry of the structure turns back to that of the diamond structure. Also, from the geometric information of the context menu, you can measure bond lengths, bond angles, and dihedral angles between selected atoms. So, I select 4 atoms. Then, bond lengths, bond angles, and dihedral angles are displayed like this. Then, I demonstrate how to substitute elements to the crystal structure. Firstly, I click the Start Modeling button of the Element Substitution. Then, I select what element to be replaced. I select silicon. Then, I select what element to be substituted. I select phosphorus. Then, I set the scaling of supercell as 2, 2, 2. Finally, I set the rate of substitution as 0.2, and click the Build button. Then, the phosphorus substituted structure is generated like this automatically. If you click the Build button again, the elements are substituted once more randomly. Then, I return to the Crystal tab. And I demonstrate how to introduce lattice defect to the crystal structure. I click the Start Modeling button of the lattice defect. Then, I select which elements to be removed. I select silicon. Then, I don't have to generate supercell, so I enter 1, 1, 1 in the input field. Finally, I set the rate of lattice defect as 0.2 and click the Build button. Then, the lattice defects are generated like this automatically. If you click the Build button again, the lattice defects are introduced once more randomly. I return to the Crystal tab. Then, I open the Cell tab. In the Cell tab, you can translate all the atoms, generate supercell model, and operate axes. Using the slide bar of the translation of cell, you can translate all the atoms in each lattice vector direction, like this. Also, you can generate supercell by the supercell function. Moreover, you can invert each lattice vector just by clicking each inversion button. In addition, you can swap each lattice vector just by clicking each swapping button. Then, I open the Lattice tab. In the Lattice tab, you can redefine the lattice vectors to generate non-diagonal supercell, and edit the lattice vectors without generating supercell. For example, I will rotate the A and B vectors by 45 degrees around the C vector, and generate non-diagonal supercell. I enter Miller indices in each input field of the superlattice to redefine lattice vectors. Then, I click the Build button. The lattice vectors are redefined automatically. However, the A and B vectors are not parallel to the X and Y axes, so I click the Refine button of the lattice vectors. The A and B vectors become parallel to the X and Y axes. Also, you can edit lattice vectors without generating supercell model. If you set the atom switch as affine positions and change the lattice vectors, coordinates of atoms are affine transformed like this. On the other hand, if you set the atom switch as leave positions and change the lattice vectors, coordinates of atoms are not transformed. Please note that the first column of atoms on the right are mirror images of atoms on the periodic boundary. Then, we will demonstrate how to generate slab models, including interface models. We use alpha alumina as an example. Then, I search and download alpha alumina structure file from Materials Project, an online database, using Materials Finder on the top right. About 80 structures in the same composition as alpha alumina on the Materials Project are displayed in tens of seconds. Then, I select the MP1143, namely, alpha alumina structure. I select the modeler function from the menu on the bottom left. Then, I open the Slab tab. In the Slab tab, you can generate slab models, molecular adsorption models, and interface models. Then, I will generate slab in 001 direction from the alpha alumina structure. Firstly, in the input file of Miller index, I enter 001 and click the Build button. Then, I set the details of the slab model. The width of the slab can be set by the slide bar of slab system, like this. Also, area of the slab can be scaled. In the input field of the area scaling, I enter 2 and click the Build button. Moreover, width of the vacuum can be changed by the slide bar of the vacuum of a side, like this. In addition, you can select the kind of surface, which NanoLabo suggests automatically. Then, I return to Slab tab. If you want to convert the slab to the primitive slab, you can do that just by clicking the Build button of the Finding a Primitive Slab, like this. Then, I undo the conversion. Also, you can invert the slab model by clicking the Build button of the upside down along C-axis, like this. Moreover, by the Build button of the Changing Vacuums Width, you can adjust the vacuum's width of the slab model. You can change the width of upper and lower vacuum, respectively. Atoms in the lower layers of the slab model are fixed during simulation as default. Fixed atoms are shown in checker pattern like this. If you want to unfix the atoms, you can do that in the Atoms tab. I select the fixed atoms and click the Start Modeling button. You can set atoms' mobility in X, Y, Z directions separately. I unfix the atoms in X, Y, Z directions, and click the End Modeling button. In the Crystal tab, you can convert the hexagonal structure to the orthorhombic structure. The slab model is in the hexagonal structure. I click the Build button of the hexagonal to orthorhombic. Then, the structure is converted to orthorhombic automatically. Also, you can convert the orthorhombic structure to the hexagonal structure just by clicking the Build button of the orthorhombic to hexagonal. The structure is converted to hexagonal automatically. Then, I open the Slab tab and generate adsorption model of oxygen molecule onto alpha alumina surface. I click the Start Modeling button of the molecular adsorption onto slab. In the tab of Selected Sorbate, you can select an atom in the periodic table or typical molecules, specifying which atom of the molecule to adsorb on the surface. I select oxygen molecule as adsorbate. In the tab of Select Site, you can select top site or bridge site or hollow site as adsorption site. I select the top site for this demonstration. You can select the single adsorption site, or set the rate of occupied sites. If you select the single adsorption site, you can move the adsorbate along the A-axis or B-axis by the slide bar, or specify the adsorption site by the site number. For this demonstration, I set the rate of occupied sites as 0.5 and click the Build button. Then, oxygen atoms are adsorbed onto the surface of alpha alumina randomly. Then, I return to the Slab tab. And, I undo the adsorption. Finally, I will generate interface model. Please note that Interface Modeler is available only in NanoLabo Pro version. Then, I click the Start Modeling button of the interface model. I will generate interface of alpha alumina and copper. So, I search and download copper structure file from Materials Project, an online database. I enter Cu in the Materials Finder on the top right. 9 structures including only copper atoms are displayed. Then, I select the MP30, which has face-centered structure. I generate 111 slab model of FCC copper by the Build button and set details of slab as before. I set the number of layers as 4. Then, I click the Build Interface button. I set the acceptable strain of each slab as 0.1. Then, lattice constants of the slabs are adjusted automatically. As needed, you can change lattice constant by the slide bar of mixing constant. Then, just by clicking Optimize button, the surfaces are matched automatically. As needed, you can translate the upper slab along the A-axis or B-axis by the slide bar and select whether to twist that by the switch. Then, I finish to model interface by this button. In this way, NanoLabo Pro version enables you to generate such an interface model easily. Then, we will demonstrate how to generate molecule models, including polymer models. We use ethane as an example. Firstly, I draw an organic molecule. I click the icon of benzene on the top right. On NanoLabo, you can draw molecule structures using JSME, which is an open-source software to edit molecules. You can draw structures such as carbon chains, carbocycles, and various functional groups easily. For this demonstration, I will generate polyethylene, so I draw ethane as monomer. Then, I save the structure. Besides, you can also search and download the structure file of ethane from PubChem using Materials Finder on the top right. Then, I select the modeler function from the menu on the bottom left. On NanoLabo, you can rotate atoms using modeler function easily. To demonstrate this, I open the Atoms tab. Then, I select atoms to be rotated and click the Start Modeling button. By clicking the Rotate Atoms button, a sphere is shown. You can rotate atoms by dragging the sphere, like this. Then, I click the End Modeling button. I undo the rotation and open the Molecule tab. In the Molecule tab, you can open the Molecule Editor, pack molecules to construct liquid models, and generate polymer models. Please note that Polymer Modeler is available only in NanoLabo Pro version. Then, I click the Start Modeling button of the packing molecules. In the right of the screen, you can set what and how many molecules to be packed. By the plus button, you can select structure files of molecules to be packed. Then, I click the Build button. Ethane molecules are packed randomly like this. If you click the Build button again, the molecules are packed once more randomly. I return to the Molecule tab and undo packing. Finally, I will generate polymer model. On NanoLabo, polymers can be packed to not only vacuum, but also other models, such as slab models. For this demonstration, I will generate polymer solid interface model. So, I open the interface model of alpha alumina and copper, constructed in the previous section. I open the modeler function. And I generate supercell model. Then, I open the slab tab and adjust the width of vacuum to pack polymers. Then, I open the Molecule tab and click the Start Modeling button of the polymer model. I click the Add Polymer button and select the structure file of ethane. I select an atom as the head side for polymerization. Similarly, I select an atom as the tail side for polymerization. Then, I set the polymerization degree as 100 and click the Build button. Polymer solid interface model is generated like this, easily. Also, you can pack multiple kinds of polymers at the same time and connect different polymers as needed. That's all for the demonstration of modeler function. On NanoLabo, complex structures can be generated intuitively and instantly. Finally, we show product information. NanoLabo can operate on Windows, Linux, and Mac OS. Calculations can be executed on not only local machine but also calculation servers or clouds. For NanoLabo, Trial Edition, Base Edition, and Pro Edition are available. Regardless of edition, you can use Jupyter interface for NanoLabo without extra charge until July 31, 2023. Separate license contract is necessary after August 1, 2023. NanoLabo Pro version 2.8 offers Interface Modeler and Polymer Modeler as additional functions. On Windows or Mac OS, node-locked license is available. On Linux, floating license is available. License prices are as follows. Please feel free to contact us for detailed information or demonstration. This is all for the movie. Please watch other movies and visit homepage from the description. Thank you for watching.